Alright, so we're going to solve a problem on Cartesian 3D vectors. This is the first of a series of problems that we might end up solving on Cartesian 3D vectors. So before that, let me very quickly rehash what we have seen in lecture on Cartesian 3D vectors and the coordinate direction angles. So let's consider Cartesian 3D vectors, and I'll first set up the Cartesian coordinate system in 3D with the x, y, z axes. So coordinate direction angles. And we call these as alpha, beta and gamma in class. And these are the angles made by the tail of the vector with the positive x, y and z directions. Right, so let's say that we have a Cartesian coordinate system. So the z-axis, then let's say this is the y-axis, and then let's say that this is the x-axis. So x, y and z. This follows the right hand rule. If I cross my fingers as I go from x to y, I get the z direction. Then let me say that there is a force vector which is drawn in space here. So this force vector is F. Now I can represent the three coordinate direction angles as follows. I have the first one here. Let me call this as gamma. This is the angle made by the tail of the force F with the positive z axis. Then I have another coordinate direction angle, which is the angle beta. This is the angle made by the tail of the force vector F with the positive y direction. And then of course I also have the angle made by the tail of the force with the positive x-axis, and this is the angle alpha. And we have further seen in class that we can write the components of the force vector F along the x, y and z directions in terms of the angles alpha, beta and gamma. For example, if we were able to say that vector F is fx in the I direction, then an fy in the j direction and an fz in the k direction, then we know from what we've seen in lecture that fx is f cos alpha, fy is f cos beta, and then fz is f cos gamma. And we can make use of these angles to come up with an identity that will be very useful in solving problems, and the identity can be written as follows. So making use of the coordinate direction angles, I can write out the force vector F as the following. So this is going to be F times cos alpha in the I, F times cos beta in the j, and an f times cos gamma in the k. Now we can write the force vector F itself as a product of its magnitude and its unit vector, which means that if I go back to the previous page, if I say that the unit vector along the line of action of this force F is going to be denoted as u suffix F, then I can write the force vector F as follows. So this is going to be magnitude times the unit vector uf is now going to be the vector sum of these components here. So that's going to be f cos alpha I, f cos beta j, f cos gamma k. And we immediately see that this force F is a common factor here, which means that we can get rid of it. And then all I'm left with is the unit vector u suffix f, which is cos alpha I, cos beta j, and cos gamma k. Now we do know that the magnitude of a unit vector is equal to unity or is equal to 1, which means that the magnitude of uf is equal to 1, or I can say that the magnitude of uf square is also equal to 1. and essentially all I'm going to do is take the magnitude of UF, making use of this expression here, which is going to be the square root of the sum of the squares of its components, but I'm squaring this, which means that I can get rid of the square root, and so essentially I'm going to have the following. So magnitude of UF square is going to be cos square alpha, cos square beta, and cos square of gamma, and the magnitude of UF square is equal to 1. This is because it's a unit vector, and so we have the following now: cos square alpha plus cos square beta plus cos square gamma is equal to 1, and this is a fairly useful result, as we will see when we solve some problems. And the basic idea being, if I know two of these coordinate direction angles, then I can find the third one, making use of this identity. And along the same lines, let's look at the following problem. So in this problem I have, this is of course a fairly straightforward problem that I'm going to solve, and basically a reiteration of the concept that we have seen. And so here is the problem. Let's say that I have the x, y and z axes as follows: x axis, y axis, and the z axis. Now I'm going to call this as the x axis, this is the y axis, and the z axis, and I have a force vector which is defined as follows. This force vector, let's say, has a magnitude of 300 newtons, and let's say that the following angles are known to us. The angle made by this force vector with the positive z-axis is given to us as 60 degrees. The angle made with the tail of this force vector with the positive x-axis is given to us as 45 degrees. And then a third angle here, which is marked as an obtuse angle, is not given to us. And the basic problem is we need to find out this angle, and we also need to express f as a Cartesian vector, which means we need to find its x, y and z components. And the basic idea is that as we can see, we are making an angle of 60 degrees between the tail of the force vector f and the z-axis, which means that this angle 60 degrees is going to be the coordinate direction angle gamma, and likewise this angle 45 degrees here is going to be the coordinate direction angle alpha. And so we know two of the coordinate direction angles, and we know that the third one is going to be an obtuse angle, so we could make use of the identity that we just looked at previously and find the third coordinate direction angle. So let's do that here. So from what we can see here, this is going to be alpha, and this guy is going to be gamma, and this is going to be beta, and we expect beta to be an obtuse angle because of the way the force vector is drawn, or the way the force vector is constructed. Here we are given the magnitude of the force vector as 300 newtons. I'm just rewriting it because my writing here is doesn't seem to be clear to me, at least. Hopefully it is for all of you out there. Alright, so I know alpha, I know gamma, I need to find beta, so I make use of my identity here. So I have cos square alpha, cos square beta, cos square gamma is equal to 1, which means that cos square 45, cos square beta, which is unknown to us, and cos square gamma, which is 60 degrees, is equal to 1. Cosine of 45 is 1 by root 2, so cosine square of 45 is 1 by 2. Cosine of 60 is a half, so cosine square 60 is 1/4. So from this we can write that cos square beta is 1 minus cos square 45 minus cos square 60, or this is 1 minus 1 by 2 minus 1 by 4, which is 1 minus 3 by 4, which is 1 by 4. And essentially we have the following: cos square beta is equal to 1/4. So cos square beta and so cos beta is going to be plus or minus square root of 1/4 is a half, and so the idea is cos beta is either plus half or cos beta is minus half. We do not know which one is the right answer, but we do have some kind of a nudge from the problem itself, which says that the angle beta is expected to be an obtuse angle, and from that sense we are going to be actually picking the negative value of cosine beta and not the positive value of cosine beta, and so since we expect beta to be an obtuse angle, this implies cos beta is minus half, so beta is the inverse cosine of minus half, which is 120 degrees. Alright, so we now have the three coordinate direction angles. We've just found them out, and the rest of the problem is fairly straightforward in the sense that we need to find the components. So the angles that we have are alpha is 45 degrees, beta freshly found out is 120 degrees, and then gamma is 60 degrees, and then we know that the vector f can be written as fxi, fyj, and fzk, and this is essentially now going to be f times cosine alpha I, f times cosine beta j, f times cosine gamma k. Notice that I did not substitute a negative sign for the j component, even though we know that perhaps the component of f in the y direction is going to be negative, because cosine beta was going to give me minus half. You still call it as a positive sign and you let the vectors take care of that, right? So this means that vector f is going to be 300 cosine 45i, 300 cosine 120j, 300 cosine 60k, or the vector f is 212.1i, 300 cosine 120 is a minus 150j, and then I have a plus 150k. Right, so these are the components of the force F, and this is the Cartesian form. Of the vector F, and before we wrap up this problem, let us very quickly take a look at how the components line up if we draw them in the Cartesian coordinate system in 3D. So here is the idea. I have the z-axis, and then I have the x-axis, and then I have the y-axis right here. Now I'm going to extend the y-axis onto the negative side, because I know that we're going to expect a negative component for the force along the y direction. So this is y, this is x, and then this is z. So I have the force which is drawn here. So this is the force F. Now I drop a perpendicular onto the xy plane here, and then I complete the triangle. So that's a 90-degree triangle, and then I take this particular vector here and then I project that onto the y and the x directions, and I see that if I do that, it intersects the x-axis at a particular location. So that's going to give me the x component of the force. Then it's going to intersect the y-axis, as you can see, along the negative direction. So that's going to give me f suffix y, and then this guy here is going to be f suffix z. Thank you.